2011 was an exciting year for astronomers. For over 200 years, mankind has known about the existence of gigantic asteroids found in the asteroid belt, but for most of that, they've only been specks in the night sky. The first asteroid to be discovered, Ceres, was found in 1801 and was added to the list of planets. A year later, Pallas was discovered, and in the following years, Juno and then Vesta. Because of this, in 1845, our solar system had 11 planets, the original 7 from Mercury to Uranus, as Neptune hadn't been discovered yet, plus the 4 asteroids. As more and more asteroids were discovered, it became clear that they couldn't all be listed as planets. A good thing too, as today there are millions of known asteroids of various shapes and sizes. However, before 2011, we had never seen any of the original 4 asteroids up close. Enter the Dawn spacecraft. Launched in 2007, it had a very special mission to explore and investigate not just one, but 2 of these large asteroids. First Vesta and then Ceres. But what did it find and discover while it was there? I'm McColgan and you're watching Astrum, and in this video we will find out everything Dawn saw and discovered around the asteroids Vesta and Ceres, and examine what made the Dawn spacecraft one of the most technically impressive probes ever produced, and how its success paved the way for NASA missions in production right now. Let's start with Dawn itself. Its trip to Vesta took 4 years, utilizing a slingshot from Mars's gravity along the way. And you'll be forgiven for not seeing anything special about this trip from this perspective. However, zooming in on the Dawn spacecraft itself reveals its very special feature, an ion engine. Ion engines had been tested already on NASA's Deep Space One, however, the way Dawn utilized it pushed this technology to a whole new level. Thanks to its ion engine, it was the first ever spacecraft to go into orbit around 2 separate extraterrestrial bodies. You see, while ion thrusters aren't very powerful, they are extremely efficient, and so can remain on for extended periods of time. Unlike chemical thrusters, which rely on reactions causing heat and pressure to push gas away from the rocket, ion thrusters simply ionize neutral xenon gas with electricity to create acceleration. These ionized gas particles rush out of the engine at 150,000 kilometers per hour, which pushes the spacecraft in the opposite direction. As the ionized gas is expended slowly, Dawn can only create so much electric charge after all. The acceleration is really slow. It would take Dawn 4 days to accelerate from 0 to 100 kilometers per hour. But over extended periods, it really adds up. Dawn was firing its thrusters for 85% of the time during the transit to Mars, expending only 72 kilograms of xenon propellant and gaining over 1.8 kilometers per second velocity. Upon reaching Vesta in July 2011, the images it started returning wowed the science community. It really was not what they were expecting. After being captured by Vesta's gravity, Dawn lowered its orbit to get a closer look at this unique asteroid. So, what made Vesta an unexpectedly nice surprise? The first thing you'll notice about Vesta is that it has an unusual shape. It kind of looks like a squashed ball. There are 2 reasons for this. The first is that it is not very big. Yes, these asteroids, although big for asteroids, are pretty tiny on astronomical scales. Vesta is not quite big enough for it to be in hydrostatic equilibrium, or in other words, to be rounded by its own gravity, as it is only about 500 kilometers in diameter. This gives it the surface area of Pakistan, about 800,000 square kilometers. You'll see how small it is if you compare it to our moon. Although, it should be noted that even at this size, it still contributes towards 9% of the total mass of the asteroid belt, which can help you appreciate just how dispersed the asteroid belt really is. The second reason for this unusual shape are the two giant impacts it experienced in its past. Estimated to have occurred over 1 billion years ago, Vesta was impacted not once, but twice around its south pole with planetary-scale objects. These impacts produced craters so large they penetrated all the way to the mantle of the asteroid. The crust has since cooled off and solidified, leaving a complex crater called Rhea Silvia. As these craters have overlapped, Rhea Silvia is the most recent and thus the most prominent crater that remains. As is typical with complex craters, terraced walls can be seen around the edge of the crater, seen in the form of huge troughs around the equator that put the Grand Canyon to shame in terms of size. Also typical of complex craters, a prominent peak can be found at the center. This peak was once thought to be the tallest mountain in the solar system, but more accurate dawn observations show that the title has returned to Olympus Mons. Although Rhea Silvia is still 20 to 25 kilometers high and over 100 kilometers across. Due to its size compared to the size of Vesta, it appears like a giant pimple around the South Pole, and it is easily visible from orbit. The two collisions that carved out the South Pole of Vesta flung a massive amount of ejecta into space. So much debris ended up in the asteroid belt that the debris has been given its own asteroid spectral type classification, namely V-type asteroids. V-type asteroids are thought to have originated from Vesta, and a lot of them can be traced back to those impacts. But these asteroids didn't just end up in the asteroid belt, they are scattered all across the solar system, and in fact, 5% of the meteorites that end up on Earth come from Vesta, known as Howardite, Eucrite, Diogenite meteorites. This is very handy, as we haven't needed a sample return mission to be able to study samples of Vesta, because Vesta has delivered some right to our front door. Their structure and composition reveal some clues about how Vesta was formed, and the Dawn mission attempted to broaden that understanding. From a combination of all the data collected, it has been revealed that Vesta is very unique in our solar system. It is the only remaining rocky proto-planet, or in other words, it is a planetary embryo that never finished forming. The theory goes that as the solar system was forming, dust from the early protoplanetary disk coalesced into thousands of different planetesimals. These planetesimals collided with each other over time, building up into the large planets we see today. Our moon is thought to have formed from such an impact, with a large planetesimal impacting Earth, called Theia. The debris from the collision coalescing in Earth's orbit, and over time rounding under its own gravity to form the moon we know today. Vesta obviously got started on its way to becoming a planet. It experienced plenty of large impacts with planetesimals. As a result of all these impacts, the heat generated by them meant that at one point Vesta had an active mantle under the surface. Even today it is believed to still have a core of iron about 220 kilometers in diameter, a core similar to the other terrestrial worlds like Mercury, Venus, Earth and Mars. However, Vesta's interior has since cooled off, meaning the interior has solidified. But because of this differentiated interior, it likely would be called a dwarf planet today, if not for those two collisions we talked about earlier. One of the criteria for a dwarf planet is that it is rounded under its own gravity. But as the collisions happened roughly 1 billion years ago, a few billion years after Vesta formed, Vesta had already cooled off too much for it to be elastic enough to return to a shape in hydrostatic equilibrium. And the reason Vesta never became a planet? Fingers are currently being pointed at Jupiter, which stole mass that would have otherwise formed Vesta, or at least disturbed enough of it to stop Vesta from ever getting going. Now, to the naked eye, Vesta does appear quite bland. This is a true color image of Vesta, appearing as you would see it. However, if you have a camera that can see in a wide variety of wavelengths of light, suddenly Vesta's true variety becomes apparent. In this composite image, the black material is likely ejecta brought by a large meteor impact. The red material is likely also from an impact, but is material that melted before solidifying again. Dawn also made some unexpected discoveries on Vesta's surface. Vesta is thought to be very dry, with little to no volatiles found in its crust. Why then has evidence of past flowing been observed? In this false color image, you can see a crater a couple of kilometers across, with a flow channel coming out of it, the different colors indicating it consists of a different material to the surrounding area. The exact origin of this material is unknown, but perhaps it was brought by the impactor and melted on collision. Another fascinating discovery was found in one of Vesta's young craters, Marcia. Near the bottom of the crater, Dawn observed something called pitted terrain. Why pitted terrain was found on Vesta is a bit of a mystery, as we have only seen it on Mars before that. However, scientists believe hydrated mineral rocks on the surface may have been rapidly heated, perhaps by another impact, releasing the water in the rocks, which exploded as the water degassed into space, leaving these craters you see here. And I would be remiss to mention that this Marcia crater is part of a chain of craters which makes up the famous snowman found on Vesta. What is interesting though is if you notice the terrain is relatively smooth around these craters. This is believed to be because a blanket of ejecta covered the region from the impacts, smoothing it over. Dawn was only around Vesta for a year before it left Vesta's orbit and moved on to the second leg of its journey towards the actual dwarf planet, Ceres. Using its ion engine, it was able to build up speed until it was finally fast enough to escape Vesta's gravity altogether, and then begin its journey towards Ceres. The anticipation within the scientific community to reach Ceres was palpable. Even with the aid of the Hubble Space Telescope, the best image we had of Ceres was this. It was still a mysterious body. What was lying in wait there? Would Dawn hold up to years in the unforgiving environment of space? And what would Ceres reveal about our own solar system? After 2 years in transit between the two bodies, Dawn finally began the approach to Ceres. As days passed, the resolution of Ceres got better and better. Details like craters could finally be resolved, and most interestingly of all, bright white dots could be seen. I remember at the time that as these images were coming in, speculation was rife about what they could be. As higher resolution images were received, it looked like the bright spots were actually 2 separate spots. And then the increased resolution revealed it was in fact several different spots. Dawn also observed the scarred nature of Ceres up close, with craters littering the surface. Although there aren't as many craters here as previously expected. Taking this into consideration, and the bright spots I already mentioned, it became clear that Ceres is not as inactive and inert as we may have previously thought. Before we delve deeper into that, let's first give you some context. Ceres is a very unusual body, seemingly out of place in the asteroid belt. Most asteroids are mainly composed of non-volatile substances, mainly rocks and metals. Ceres, on the other hand, has a similar composition to that of a comet. It is, in other words, an icy world. However, being this close to the Sun, any ice directly on the surface sublimates. This means that the surface crust is rocky, yet porous, with water locked into the gaps, with a ratio of about 90% rocks and 10% water. Beneath the surface, there is believed to be a muddy mantle, and a large core of hydrated rocks, such as clays, where rock and brine are mixed together at a 50-50 ratio, although this has been hard to confirm. Other models suggest the core could be a lot drier and smaller, with a greater ratio of water to be found in the mantle. Either way, water is definitely present in Ceres in large quantities, making up perhaps 50% of its total volume due to Ceres' low density. And it's this water that perhaps renews the surface of Ceres, albeit over extremely long timescales. You see, these bright spots are what is known as cryovolcanoes. Unlike regular volcanoes, which spew lava out from the mantle, cryovolcanoes erupt water. This is a 3D model based on Dawn data of the biggest bright spot on Ceres. Water on Ceres is packed full of salt, meaning that when a cryovolcano on Ceres erupts, the water sublimates and the salt is left behind. This was directly observed over the brightest patch on Ceres, known as Spot 5, as a haze was periodically seen over this area, indicating that water there had sublimated. These bright spots darken over time from exposure to the sun through space weathering, so it's likely that many old cryovolcanoes exist on the surface of Ceres, although we can now only see the most active and recent ones. However, the ones we see aren't just limited to the bright spots we've looked at so far. There are many of them dotted around the dwarf planet. Water was discovered in other regions around Ceres too. Due to Ceres' very minimal axial tilt of only 4 degrees, some craters at its poles are in perpetual darkness. The bottom of these craters never see direct sunlight, meaning water ice can exist here without sublimating. This is very similar to our moon, where water ice is thought to have been trapped at the bottom of perpetually dark craters for billions of years. What else did Dawn spot on the surface of Ceres? As I mentioned, it saw plenty of craters, each with unique characteristics. Some were very round and defined. Others had scarps along the crater floor. There are plenty of examples of complex craters with tall peaks in the center. There was even evidence of crater rims collapsing. For example, this rock having fallen away from the crater walls. Smaller rocks were also spotted having fallen down crater walls, evidenced by the trails they left behind. I also love these photos taken at an angle, pointed along the limb of the dwarf planet. To me, these give a much better idea of the scale of the features we are looking at, although without an atmosphere to provide a sense of depth, it is hard to judge sizes in images like these. Fractures were also spotted all over Ceres, indicating there have been stresses in the crust. Some of them are relatively young, perhaps only a few 100 million years old. Some of them come in the form of grooves and troughs, where the crust has been stretched, and other fractures can be seen in the form of rows of mountains, where the crust has been compressed. One particularly unusual feature was spotted on Ceres called Ahuna Mons. It's a mountain about 20 kilometers wide and 5 kilometers high, but what's unusual about it is how it just sticks up from the surrounding area with no apparent cause. It would be less unusual if there were other features like this on Ceres, because then it could be said it's a global phenomenon. But it's the only thing like it on the entire world. The best bet we currently have is that it is an old cryovolcano, formed because of a large impact directly on the other side of the dwarf planet. Seismic waves from a large impact can propagate through the crust of a planet, and where the waves meet again on the opposite side is known as the antipode. Known antipodal regions around the solar system tend to have some kind of weird terrain, like that found on Mercury. Ahuna Mons could fit this description, with seismic waves from an impact on the opposite side of Ceres triggering volcanic activity here. If it is a cryovolcano, it actually has some analogues around the solar system. It would be classified as a dome volcano, similar to Mount St. Helens, or to some domes seen on Mars. In 2018, Dawn concluded its mission, having been a tremendous success. It finally ran out of propellant, which meant it can no longer stay pointed at Earth to send back data or receive commands. It's been left in a stable, derelict orbit around Ceres, a monument in space that will remain there for at least another 20 years. Dawn's discoveries and data will be at the heart of asteroid research for many years yet, but it also leaves behind another legacy. Its ion engines were the key to its success, and there are now many other missions that currently use them. SpaceX's Starlink satellites have ion thrusters on board, as well as China's Tiangong space station. ESA's Bepi-Colombo mission will be using them to get to Mercury, and NASA's DART mission is using them to get to the binary asteroid system Didymos and Dimorphos. In the dark, frigid void beyond Neptune lies a vast and mysterious region where the ancient remnants of our solar system's birth drift silently through the darkness, perfectly preserved by the deep freeze of space. To reach this shadowy expanse from Earth, we must travel past the rocky planets, flying by Mars and then beyond the swirling storms of Jupiter and Saturn. Farther still, out beyond the blue giants, Uranus and Neptune, we finally reach our destination. Welcome to the Kuiper Belt, a vast ring of icy debris encircling our solar system like a frozen halo. This isn't just a collection of distant rocks, it's a time capsule from 4.6 billion years ago, holding the untouched building blocks of our cosmic neighborhood. It is home to several dwarf planets and mysterious objects that have left many astronomers scratching their heads. I'm Alex McColgan and you're watching Astrum. Join me today as we explore the worlds lurking in the shadows of our solar system and piece together clues about its history, about planetary formation, comet activity, and even the origins of life. Before we knew for sure that the Kuiper Belt was real, astronomers suspected that something existed beyond Neptune. For decades, everyone's favorite dwarf planet, Pluto, was thought to be an isolated object in the outer solar system, but something didn't add up. Its small size and unusual orbit suggested that Pluto wasn't alone, and that maybe it was merely one of a number of yet-to-be-discovered distant objects. In 1951, astronomer Gerhard Kuiper predicted the existence of a belt of icy objects just beyond the orbit of Neptune, but without telescopes powerful enough to detect these objects, the idea remained theoretical for decades. That changed in 1992, when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object, known as 1992 QB1. Pluto and its moon Charon were both discovered before 1992 QB1, Pluto in 1930 and Charon in 1978, but these objects were only confirmed as KBOs after the 1992 KBO. Since then, thousands more Kuiper Belt objects have been identified, populating this distant region beyond Neptune. To grasp the true scale and position of the Kuiper Belt, let's imagine we're traveling in a spaceship, starting from the Sun and moving out towards the outer edge of our solar system. As we move along our journey, let's compare the Kuiper Belt to both the more well-known asteroid belt and the less well-known Oort cloud. Starting near the Sun, we zip past the rocky planets, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter, we see the asteroid belt, made up of the leftover materials from when our planets formed. A thin, spread out ring of rocky debris, the asteroid belt is about 2.2 to 3.2 astronomical units away from the Sun and about 1 astronomical unit wide. As a reminder, 1 astronomical unit is equivalent to the distance from the Sun to the Earth. Most of the known asteroids reside in this part of our solar system, ranging in size from the largest asteroid, Vesta, at 525 kilometers wide, almost the distance from London to Belfast, to the smallest objects, some of which are just tens of kilometers across. However, despite residing in such a large space, the total mass of all of the asteroids in the whole asteroid belt combined is only about 3% of the mass of the Moon. Beyond the asteroid belt, we encounter the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, colossal worlds that dominate the outer solar system. Finally, as we pass Neptune's orbit at 30 astronomical units, we reach our destination, an even more remote, icy frontier, the Kuiper Belt. This vast expanse stretches from 30 to 50 astronomical units and is home to a range of intriguing objects, from frozen relics of the early solar system to dwarf planets including Pluto, Haumea, Eris, Makemake, and countless other smaller objects. Like the asteroid belt, the Kuiper belt contains ancient debris from our early solar system. In fact, Kuiper belt objects are considered some of the oldest surviving pieces of our solar nebula that originally formed the planets of our solar system. And so, at one point in the very distant past, these stray pieces might have been able to come together to form yet another planetary body. However, Neptune's gravity prevented the icy objects from coalescing and never allowed them to form something new. Unlike the asteroid belt, which is primarily made of rocky material, the Kuiper belt consists of mostly frozen methane, ammonia, and water ice, forming a frozen, thick, donut-shaped ring of debris. The Kuiper belt contains hundreds of thousands of large icy bodies bigger than 100 kilometers across, and more than 1 trillion comets, not to mention smaller debris and dust. And the average distance between objects is so large it can be hard to imagine. Each of those objects is, on average, between 0.02 to 0.1 astronomical unit apart. Imagine 10 million kilometers between objects. Here in the dim outer reaches of our solar system, these icy bodies drift in near silence, preserving vital clues about the origins of planets and comets. But it doesn't end there. That was just the main region of the Kuiper belt. Overlapping the outer edge of the main region is another area of Kuiper belt called the scattered disk, which continues out to nearly 1,000 astronomical units, with some Kuiper belt objects on orbits that reach even farther beyond that. So while the asteroid belt and Kuiper belt share some similarities, as you can see, one is vastly more expansive than the other. And while we may have reached the end of the Kuiper belt, there's still another massive structure that surrounds every other object and belt I've mentioned so far. In a recent video, I talked about the Oort cloud, the colossal structure of orbiting icy debris that encircles our entire solar system. It's so jaw-droppingly far away that even our most powerful telescopes can't catch a glimpse. So how do those two structures, the Oort cloud and the Kuiper belt, differ from each other? For one, the Kuiper belt is thousands of times closer to the Sun than the center of the Oort cloud, which is theorized to stretch from 2,000 to 100,000 astronomical units. Another major difference is that the Kuiper belt is donut-shaped, while the Oort cloud is spherical, like a gigantic bubble of swarming debris. But something these structures do have in common is that they are both sources of the celestial phenomenon that we know as comets. The Oort cloud is the source of many long-period comets, while the Kuiper belt is where some short-period comets are born. While the Kuiper belt today is one of the most massive structures in the solar system, it's just a small fraction of what it once was. Originally, altogether, it probably contained 7 to 10 times the mass of Earth, but the shifting orbits of the 4 giant gas and ice planets caused most of that to be lost to space. What remains is no more than about 10% of Earth's mass. Not only that, but the Kuiper belt today continues to slowly erode away. As objects occasionally collide and break apart, smaller fragments are left in their wake, and some of the resulting dust is blown out of the solar system by the solar wind. Sometimes these collisions, or Neptune's gravity, will cause Kuiper belt objects to head on a new path towards the Sun, creating short-period comets which have orbits of less than 200 years. Over time, the Sun's radiation causes comets to shed material, producing the spectacular tails we see from Earth. Several famous comets originate from the Kuiper belt or its scattered disk, including Halley's Comet with an average orbital period of 76 Earth years, or Comet Shoemaker-Levy 9, which broke apart and smashed into Jupiter in 1994 in the first ever observed collision of 2 solar system bodies. As we all know, Jupiter survived, but the impact was visible from Earth and was quite a spectacular sight to behold. You can see it out for yourself if you check out my video on the aftermath of this collision. You may also have heard in the news recently about a near-Earth asteroid named 2024 YR4. While there is a very, very small chance of this asteroid colliding with our moon, or even a smaller chance of it impacting Earth, the short-period comets originating from the Kuiper Belt pose no immediate threat to us in the next 100 or more years. In other words, you don't need to worry about that. Despite the Kuiper Belt being just a small remnant of what it once was, it still offers a nearly endless frontier of objects for us to explore. And unlike the Oort cloud, which we have not been able to visit yet, we have been to the Kuiper Belt. While most of what we know about the Kuiper Belt comes from ground-based telescopes and the Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have actually been there. It performed a flyby of the dwarf planet Pluto and Kuiper Belt object 2014 MU69, which was later officially named Arakoth, meaning sky, in the Native American Powhatan or Algonquian language. This flyby of Arakoth in 2019 was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto, with the New Horizons spacecraft getting as close as about 3,500 kilometers above the surface of the object. And even among the swarm of mysterious objects that make up the Kuiper Belt, Arakoth still managed to surprise the New Horizons team. Its strange shape was unlike anything we had ever seen in our solar system. Arakoth is a small icy KBO known as a contact binary, composed of two distinct lobes that at some point merged into one body. Its shape resembles a flattened snowman. At just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick, you might not think there's much to learn from this relatively tiny object. But what Arakoth lacked in atmosphere and diverse geology, it made up for in its unique structure. The bizarre pancake snowman shape of this Kuiper Belt object provides crucial insights into how planetary building blocks came together in the early solar system, and how planets may have formed. Arakoth's shape seemed to give it a counterintuitive gravity field and rotation, and several papers published since the flyby have led to an almost undeniable truth about how planetesimals form, something the New Horizons team didn't expect. Planetesimals form when smaller objects come together to make larger bodies, which may eventually combine to create a planet. Until now, there have been two competing theories: hierarchical accretion, which proposed that small objects would crash into each other at high speeds until they created something bigger, and local cloud collapse, where nearby objects would slowly come together because of their gravitational attraction, thereby forming larger and larger bodies. And now, thanks to the Arakoth flyby and important research into the object's geology, geophysics, composition and formation, we can be fairly certain that the theory of local cloud collapse is correct. The object's smooth surface and the lack of fractures from stress confirm that the cosmic snowman formed at low speed. Alan Stern, a planetary scientist and the lead for the New Horizons mission, said that the evidence was so strong, we've decisively solved a multi-decade debate about how planetesimals form. And thanks to New Horizons, we get to see the most famous Kuiper Belt object, Pluto. The spacecraft performed a flyby in 2015, allowing us to get up close and personal like never before and take those stunning images. The mission collected observations of Pluto and Charon, the dwarf planet's largest moon, and was able to collect data on Pluto's other satellites, Nix, Hydra, Kerberos, and Styx. Of course, we've all seen the stunning photographs of Pluto's heart-shaped surface region, also known as Tomba Regio. But did you know that the heart-shaped feature is actually a glacier? The western lobe of the heart, named Sputnik Planitia, after Earth's first artificial satellite, Sputnik 1, is a vast nitrogen glacier that stretches 1,000 kilometers wide and 4 kilometers deep.
and is undoubtedly the largest known glacier in the solar system. The eastern lobe of the heart gets its light color from nitrogen that is carried from Sputnik Planitia and deposited as ice. Not only did we get stunning images of Pluto, but the data from New Horizons forever changed how we understand our favorite dwarf planet. It revealed that Pluto is far more complex than we previously thought, and offered clues to the origin of its heart-shaped feature. The data led some to believe that Pluto's heart-shaped region could be explained by an internal water-ice ocean. However, a recent study led by astrophysicist Harry Valentine from the University of Bern has revealed another, more likely culprit. The heart shape may have been caused by a low-velocity impact that left a gigantic splatter across the surface of Pluto, creating the western half of the heart shape. This impact would have come in at an oblique angle, as in not straight on. Imagine throwing a water balloon across dry pavement in the same way you might skip a stone across a pond. When the balloon scrapes the pavement, it pops, leaving an elongated splat of water across the pavement. This kind of angled, low-velocity impact is similar to how the western lobe of Pluto's heart feature may have been created. But it's not just Pluto that we get to see up close. The images of Pluto's moon Charon were also incredible. Can you make out the enormous equatorial tectonic belt? Its existence suggests a long-gone water-ice ocean on Charon. So what comes next in our quest to understand the Kuiper Belt and, consequently, to understand our solar system? New Horizons is expected to exit the Kuiper Belt sometime between 2028 and 2029. And while there is no current target for a further flyby, it is possible that NASA identifies another suitable target. New tools like the James Webb Space Telescope could help us to further analyze the composition of Kuiper Belt objects. And perhaps in the distant future, a robotic mission might allow us to land on one of these mysterious objects, or even collect a sample for a return mission back to Earth. Who knows what else we'll discover out there in this vast frozen frontier. As technology advances, future missions will hopefully push deeper into the Kuiper Belt, revealing more of its long-held secrets, one icy world at a time.
What if I told you that there is a colossal structure that begins at the edge of our solar system? One that encircles our sun and all of the planets, but we've never seen it. A shell made up of billions or even trillions of ancient icy chunks the size of mountains marks the outermost boundary of our solar system, or so we think. Jaw-droppingly far away, beyond the reach of even our most powerful telescopes, the Oort cloud is a region shrouded in mystery and speculation where the sun's influence grows faint as it brushes up against the void of interstellar space. What exactly is this Oort cloud? If we've never directly observed it, how do we know it's out there? And why do some people question its existence? Let's find out. I'm Alex McColgan and you're watching Astrum. Join me today as we venture to the farthest reaches of our solar system and beyond to construct an image of this unseen astronomical wonder. You've probably heard of the asteroid belt, and maybe even the Kuiper Belt. At two different locations in our solar system, these roughly donut-shaped bands of debris each move in the same direction, and more or less on the same orbital plane as the planets around our sun. The asteroid belt is the closest to the sun of these two debris rings, located between Mars and Jupiter, and consists of millions of orbiting asteroids. The Kuiper Belt, on the other hand, was first proposed by astronomer Gerard Kuiper as the origin of short-period comets in the mid-20th century. It is a massive field of icy debris out past Neptune. Occasionally, a piece of Kuiper Belt debris will get pushed by gravity, sending it on a new orbit closer to the Sun. In some cases, this creates a new short-period comet. These comets have orbits of less than 200 years, and are often predictable as they continue to make subsequent orbits around the Sun. At the same time that Kuiper was investigating short-period comets, a Dutch astronomer named Jan Oort was contemplating the origin of long-period comets. Few scientists of the 20th century made more contributions to astronomy than Oort. In 1927, he calculated our place in the Milky Way galaxy, and in 1932, he was the first to find evidence of dark matter, to name a few examples of his discoveries. In 1950, Oort was the first to theorize the existence of a thick bubble of swarming, icy debris that surrounded our entire solar system, now known as the Oort cloud. But unlike the asteroid belt and Kuiper belt, it's still yet to be directly observed. To understand this theory, let me explain what led Oort to this proposition. Unlike comets with short orbits, such as Halley's Comet with an average period of 75.3 years, or Comet Encke with a period of just 3.3 years, long-period comets were unpredictable. For one thing, their orbital periods were so long that in some cases they could take as many as 30 million years to complete one orbit. And curiously, these comets came from all different directions and had various orbital inclinations. It was a mystery on the grandest of scales, but Oort noticed a few things that all of these long-period comets had in common. Their orbits indicated that these comets weren't coming from far out in interstellar space, but that their origin had to be closer to home. However, as I'll explain in a moment, not too close to home. So, if these long-period comets weren't coming from the Kuiper belt and weren't coming from far out in interstellar space, where were they coming from? Oort found a peculiar similarity among the orbits of these comets, one that might provide the answer to that question. The point in a comet's orbit where it is most distant from the Sun is called the aphelion. Oort noticed that all observed long-period comets seem to have an aphelion that all grouped around a certain distance, around 7.5 trillion kilometers from the Sun. That's right, trillion with a T. As you can see, when it comes to the distances I'll be talking about in this video, our typical units of measurement fall a bit short. So instead of using kilometers, I will switch to astronomical units. One astronomical unit, or AU, is defined as the distance between Earth and the Sun, or about 150 million kilometers. So Earth is 1 AU from the Sun. The aphelion grouping that Oort noticed, where the long-period comets reached their farthest orbital distance from the Sun, was about 50,000 astronomical units. To help picture the orbits of these long-period comets, keep in mind that the outermost planet in our solar system, Neptune, is around 30 AU from the Sun, or about 4.5 billion kilometers. The main region of the Kuiper belt extends from Neptune's orbit at 30 AU out to around 50 AU, but recent evidence from NASA's New Horizons spacecraft suggests a second region of the Kuiper belt called the scattered disk, which continues to around 1000 AU. It's with these key findings from observed comets that they didn't come from far out in interstellar space, the orbital distances clustered around 50,000 AU, and the fact that they arrived from any direction and orbital inclination, that Oort theorized a special spherical swarm of icy debris that he believed to be the origin of long-period comets. In the years since then, mathematical models have shown agreement with the Oort cloud theory, and astronomers have further theorized various mechanics by which the Oort cloud came to be in its current state. The leading idea is that the Oort cloud formed from ancient debris, leftovers from when our planet formed 4.6 billion years ago. After the planets formed, the surrounding area was still rich with these smaller, leftover chunks of material called planetesimals. The gravity from these early planets then scattered the leftover material in every direction. Some material was flung out of the solar system entirely, but a significant portion was sent into seemingly random, eccentric orbits around the Sun. These scattered planetesimals had eccentric enough orbits that they were influenced by gravitational forces outside of our solar system, while still remaining captured in our Sun's orbit. And it's believed that this is how these billions or trillions of icy chunks came to be part of the Oort cloud. Gravitational perturbations can force Kuiper belt objects out of place, creating short-period comets. We think that similar forces are what send Oort cloud objects into elliptical orbits with the Sun, thereby creating long-period comets. These perturbations could be caused by passing stars or molecular clouds or tidal forces from the Milky Way itself. In fact, about 70,000 years ago, Schultz's star gained the title of the star that came closest to our solar system, actually grazing the outer region of the Oort cloud. But luckily for us, it didn't cause any catastrophic disruptions to the Oort cloud or our solar system at large. Schultz's star is a low-mass binary system made up of a red dwarf and a brown dwarf companion. So 10 millennia ago, even at a much closer distance to the Oort cloud, the gravitational influence of this binary star was significantly weaker than that of our much more massive Sun. However, while most objects experience little to no impact during the low-mass star's brief encounter with the edge of the Oort cloud, numerical simulations from 2018 concluded that Schultz's star is believed to have nudged at least some objects out of place, creating and influencing the trajectory of some long-period comets. But the Sun has been around for over 4 billion years, and that's a lot of time for other close encounters with stars in the distant past. Could these interactions have prevented the Oort cloud from forming? Our models suggest no. However, Oort cloud material may get exchanged with passing stars over eons. You see, other, more recent numerical simulations have suggested that Oort clouds could exist around other stars too. Our Oort cloud may also have both an inner and an outer region, each with its own distinct shape. Some scientists suggest that the inner region may be more like a disk, similar to the donut shape of the Kuiper belt, while the outer region is suggested to form the spherical shell more widely associated with the Oort cloud. Altogether, the inner edge of this two-region Oort cloud may be 2,000 astronomical units from the Sun at its closest, with the far edge stretching all the way out into interstellar space, potentially reaching as far as 100,000 astronomical units from the center of our solar system. This means the Oort cloud could extend more than 1.5 light years across. To put that into perspective, since we're talking about very, very large distances, consider Voyager 2 spacecraft for a moment. As of the publication of this video, Voyager 2 has traveled to a distance of about 139 astronomical units from the Sun since its launch from Earth at 1 AU in August of 1977. That's about 3.3 AU per year, or about 56,000 kilometers per hour. It's the second farthest human-made object in space, just after Voyager 1. In August 2007, Voyager 2 passed beyond the boundary of the heliosphere, the outermost layer of the Sun's atmosphere. It extends out beyond the planets, and 3 times further than the distance to Pluto. Outside of the heliosphere, the Sun's constant flow of charged particles, called the solar wind, is finally impeded by the interstellar medium. And in November 2018, Voyager 2 finally crossed the final layer of solar turbulence called the heliosheath and continued on into interstellar space. Despite passing beyond the heliosphere and well past the main Kuiper belt, Voyager 2 would still need to travel for another 300 or so years just to reach the innermost edge of the Oort cloud. That's how far away it is. And to fly through the Oort cloud, that could take another 30,000 years. Even when traveling at 56,000 kilometers per hour, it still takes all that time just to travel around 1.5 light years. If you've ever wondered why interstellar or intergalactic space travel is difficult, keep in mind that our nearest stellar neighbour is Proxima Centauri at around 4.25 light years away. However, some still question the existence of the Oort cloud, mainly because we're unable to directly observe it. Another argument has been made that long-period comets may come from other places, such as interstellar space. And in fact, the first observation of an interstellar comet, one that had origins from outside our Sun's influence, was made in 2019 by amateur astronomer Gennady Borisov. Professional astronomers joined in to collect data on comet Borisov, named after its first observer. They found an unusual composition, a higher concentration of carbon monoxide than the average comet originating from our own solar system, suggesting that this comet may have formed in the presence of a red dwarf, a different type of star than our Sun. And yet, the vast majority of astronomers agree that the Oort cloud is really out there, despite the fact that we've never laid eyes on it. Plenty of indirect observations and mathematical models show great support for the theory, and the evidence continues to add up. But why is it exactly that we've never been able to see the Oort cloud? After all, with telescopes we can see stars far beyond our own solar system, and even the shapes of distant galaxies. The difference is size and light. Think about it. A piece of Oort cloud debris is roughly the size of one mountain on Earth. Let's consider Mount Everest at around 9 kilometers tall. Now consider the Oort cloud's innermost boundary begins somewhere around 3000 AU, or roughly 450 million kilometers from the Sun. The distance from the Sun to the nearest piece of Oort cloud debris is 50 million times the size of the debris. Talk about looking for a needle in a haystack. But more crucially even, is that stars and galaxies give off light, but Oort debris does not. The planets are relatively close to the Sun, so they are able to reflect the Sun's light and therefore are visible. Likewise, the asteroid belt and even the Kuiper belt are close enough to the Sun that we can use telescopes to directly observe their debris. But outside of the heliosphere, the Oort cloud is just too far and too dark for our telescopes to catch a glimpse. Despite the Oort cloud's gargantuan footprint and pivotal role in shaping our understanding of the origin of many long-period comets, for now we can still only infer its existence through mathematical models and indirect observation. But don't let our inability to make direct observations discourage you from following the evidence. I can think of a few other times in history when scientists put forth monumental theories despite a lack of direct observation. For example, in the 16th and 17th centuries respectively, Copernicus and Galileo put forth the theory that the planets orbited around the Sun, contradicting a widely held belief at the time that the Earth was the center of the solar universe. Their theory of a heliocentric solar system was not based on direct observation, but rather on indirect observation of the orbit of the planets. As we know, that theory turned out to be spot on. That's the thing I love about science and the pursuit of knowledge. There's always more to learn. The farther we travel through time, the better our understanding of the solar system will get. Who knows? Maybe in 100 years, future astronomers will have found a way to prove the existence of the Oort cloud once and for all. Or maybe they'll have found a whole new explanation for long-period comets. Until then, the Oort cloud remains one of astronomy's most compelling enigmas.
There are literally millions of asteroids in our solar system, and surprisingly there are also many different types. They are not just found in the asteroid belt, but they are, in reality, darting all around our solar system. My name is Scott Manley and you're watching Astrum, and today we're going to discuss some of the most interesting asteroids we've discovered so far. But what exactly is an asteroid? And what's the difference between an asteroid and a comet? Well, an asteroid is a minor planet or a small solar system body. A minor planet is an astronomical term for a small solar system body which is not outgassing. They're generally rocky or metallic, but may contain volatile compounds underneath the surface protected from sunlight. Comets, on the other hand, have these volatile materials near the surface, and when they are heated by the solar radiation, they produce coma and tails. This distinction between asteroids and comets has existed for over a century. However, the lines are a lot more blurred than we first thought. The level of activity from a body is largely dependent upon its distance from the Sun. Objects which exist far beyond the orbits of Neptune are inert all year round, but if they were to be brought in close to the Sun, they would turn into comets. So just keep that in mind while watching. In this video, we will only talk of asteroids which have orbits in the inner solar system, or in other words, between the Sun and Jupiter. Not all asteroids are the same. There's obviously a difference in size, from dust particles all the way up to the biggest known asteroid, which is almost 1,000 kilometers in diameter. Asteroids are also classified based upon their spectrum or color, which often indicates what the asteroid is made of. There are three main spectral categories that most asteroids fall into. There are the C group, which are dark carbonaceous asteroids, the S-type, which are stony or silicaceous asteroids, and the M-types, which are metallic asteroids. There are other types too, but these are the three main categories. We might mention some of these as the video progresses, but they are basically variations on these three groups that I just mentioned. Now, let's count down the top 10 most interesting asteroids. 2005 VX3 is the minor planet with the largest aphelion that we know of. At its closest approach to the Sun, it's only 4.1 AU away, which is inside the orbit of Jupiter, but when it's furthest away, it has a massive estimated heliocentric distance of 3000 AU from the Sun. Because of this, it is estimated to have the largest orbital eccentricity of any known minor planet. The last time it was seen was January 2006 when it came to perihelion, and it probably won't be seen again for another 30 to 40,000 years. It could well be a dormant comet that is not seen outgassing. It may have made closer approaches to the Sun in the past, which would have removed most of the volatile icy materials, hence why it has no tail and why we don't recognise it as a comet. It is estimated to be about 7 kilometers in diameter. Number 9. 99942 Apophis is a near-Earth asteroid which caused a bit of a stir in December 2004 because the initial observations indicated a probability of about 2.7% that it would hit the Earth on April 13, 2029. Not to worry, however, as additional observations improved this asteroid's predicted orbit, which eliminated the chance of collision in 2029. However, the possibility remains that during this very close encounter with Earth, Apophis could pass through what's called a gravitational keyhole, a small region of no more than about 800 meters wide, that would alter its orbit sufficiently to put it on a future impact scenario exactly 7 years later in 2036. This possibility kept it at level 1 in the Torino impact scale until August 2006, when the probability that Apophis would pass through this keyhole was determined to be very small. Now at this point in time, the possibility has effectively been ruled out. Apophis did however set the record for highest rating on the Torino scale, reaching a level 4 at one point. Had it hit Earth, the estimated kinetic energy would have been about 750 megatons, 13 times more powerful than the largest hydrogen bomb ever exploded. Apophis is a stony S-type asteroid. The most recent observation of it in 2013 estimated the asteroid to be about 325 meters across. Interestingly, an asteroid the size of Apophis is expected to hit Earth about every 80,000 years on average. Let's hope the next one isn't too soon. Number 8. 25143 Itokawa. This is a Mars-crossing asteroid. In other words, it crosses inside the orbit of Mars. It was the first asteroid to be the target of a sample return mission, accomplished by this Japanese space probe Hayabusa, and it is the smallest asteroid ever to be photographed by a spacecraft, being only 500 meters across at its longest point. It is an S-type asteroid, but it may be a contact binary. That means it would effectively be two separate asteroids which have merged over time. It has very little in the way of impact craters and is covered in boulders, described by the mission team as a giant rubble pile. They estimate its average density to be about 1.8 grams per cubic centimetre, which means it can't possibly be solid rock, but more like fragments of gravel that have built up over time. Interestingly, its gravity wasn't strong enough to enable the space probe to go into orbit around it. Instead, they parked the space probe next to the asteroid and orbited the Sun alongside it. In 2010, they landed on the asteroid and successfully returned dust samples from its surface to Earth. Number 7. Pallas. Pallas is the second asteroid to have been discovered after Ceres. When astronomers were looking for Ceres again after its initial discovery in the early 1800s, they accidentally found Pallas instead, which coincidentally was near Ceres at the time. When Pallas was discovered, it was counted as a planet, as were other asteroids in the early 19th century. The discovery of many more asteroids after 1845 led to their reclassification as minor planets. Pallas is one of the largest asteroids in the solar system. It is estimated that it comprises 7% of the mass of the asteroid belt, and its diameter of 544 kilometers is slightly larger than that of Vesta. But it is about 10 to 30% less massive than Vesta, placing it third amongst the known asteroids in terms of mass. Pallas is a C-group asteroid, which means it has a very low albedo, giving it a dark surface that reflects only 4% of the light falling on it. That's the equivalent of fresh asphalt. At its brightest, it may be visible with binoculars, but not with the naked eye. The Palladian orbit is inclined at 34.8 degrees to the plane of the solar system, meaning that it's practically inaccessible to any spacecraft which might want to rendezvous and investigate its slope more closely. Number 6. 10199 Chariklo. Now this asteroid technically shouldn't be on this list, but we had to include it due to its remarkable ring system. The reason it shouldn't be on this list is because it's what we call a centaur, a minor planet that orbits within the orbits of outer planets, in this case Uranus and Saturn. It is the largest known centaur, being over 300 kilometers in diameter, and like I mentioned, it has a ring system, much like on Saturn, but just on a much smaller scale. In 2013, it was discovered that it has two rings, one 7 and the other 3 kilometers wide, both being about 9 kilometers apart. It is the smallest known object to ever have rings. In fact, because it's so small, these rings shouldn't be stable at all. Either they are actively contained by Sheppard moons, or they will slowly wane and disperse over the next few million years. Number 5. Lutetia. Lutetia is a large M-type asteroid. It has a retrograde rotation and is found in the asteroid belt. It measures about 100 kilometers in diameter and has one of the greatest densities of any asteroid observed. Its average density is estimated to be about 3.4 grams per cubic centimeter, meaning that it must be made of metal-rich rock. But rather bizarrely, there is little evidence of metal on the surface, and its colour resembles more a C-group carbonaceous asteroid. Due to the density, though, we know that it must indeed have metals contained within it, and it is speculated that the metal-rich core of the asteroid is surrounded by a 3-kilometer thick layer of dust and rubble we call regolith. This theory is backed up by the way that impact craters on the surface have softened outlines. Lutetia has an irregular shape and is heavily cratered, with the largest impact crater reaching 45 kilometers in diameter. Number 4. 433 Eros is an S-type asteroid approximately 34 kilometers long, and it is the second largest near-Earth asteroid after 1036 Ganymede. Eros is a Mars-crossing asteroid, and it was the first asteroid known to do so. Objects of this kind's orbit can remain there only for a few 100 million years before the orbit is perturbed by the gravity of Mars. Eros may evolve into an Earth crosser with as short an interval as 2 million years, and apparently has roughly 50% chance of doing so in the time scale of about 100 years, which means it will eventually become a potential Earth impactor, comparable in size to the impactor that created the Chicxulub crater that led to the extinction of the dinosaurs, the equivalent of a 100 teraton weapon. The Near Shoemaker probe visited Eros in 1998 and 2000, finishing its mission by actually landing there in the surface. It was not designed to be a lander. And if that doesn't get you interested in Eros, The data collected suggested that it contains about 20 billion tons of rare metals such as gold and platinum. Number 3. 243 Ida. It is a stony S-type asteroid found in the asteroid belt. In 1993, Ida was visited by the spacecraft Galileo as it was bound for Jupiter. Ida has an average diameter of 31.4 kilometers, and it is irregularly shaped and elongated, apparently composed of two large objects connected together. Its surface is one of the most heavily cratered in the solar system. Its density is about on average for an asteroid at about 2.6 grams per cubic centimeter. Unlike all asteroids, it has very weak gravity. Theoretically, you could jump from one end of the asteroid to the other in one go. If you exceeded 20 meters per second, you could actually escape the asteroid's gravity altogether. But what is most fascinating about Ida is its moon, Dactyl. Being only 1.4 kilometers in diameter, it is about 1/20th of the size of Ida. It was named after the Dactyls, creatures which inhabited Mount Ida in Greek mythology. Dactyl and Ida share many characteristics, which imply they came from the same place. We know of other asteroids which have moons, but Ida is the only one that we have high-definition imagery of. Number 2. Vesta. Vesta is the second most massive object in the asteroid belt after the dwarf planet Ceres, with a mean diameter of 525 kilometers. Vesta is the last remaining rocky proto-planet, which means that it has a differentiated interior similar to the ones formed by the terrestrial planets. Numerous fragments of Vesta were ejected by collisions billions of years ago, and these left two enormous craters occupying much of Vesta's southern hemisphere. Debris from the impact has since fallen to Earth as Howardite, Eucrite, Diogenite meteors, which have a valuable source of information about Vesta. Other fragments stayed in a similar orbit to Vesta, and there are so many of them that, along with Vesta, they have been given their own class of asteroid, the V-type. Vesta is the brightest asteroid visible from Earth. It also has the tallest mountain in the solar system, called Rhea Silvia. NASA's Dawn spacecraft entered orbit around Vesta in 2011 for a one-year exploration. There is now a huge amount of data on this asteroid, and researchers are still sifting through this data 3 years after Dawn left. Number 1. Ceres. And finally, the only dwarf planet in the asteroid belt. Ceres for many years was considered a planet due to its size, which is about 960 kilometers in diameter. Composed of rock and ice, Ceres is estimated to make up about 1/3 of the mass of the entire asteroid belt. It is so big, it is the only asteroid rounded by its own gravity, but even though it was the biggest asteroid, in planetary terms it is still rather small. Our moon, in comparison, is huge. It is believed that Ceres has a rocky core and icy crust, and may have a remnant internal ocean of liquid water under a layer of ice. It is carbonaceous C-type asteroid, meaning that the surface is probably a mixture of water, ice, and carbonates and clay. Emissions of water vapour have been detected from Ceres. This was unexpected, as asteroids in the asteroid belt do not usually give off vapour, as that's more like a comet. The NASA spacecraft Dawn entered orbit around Ceres in 2015 after finishing its mission around Vesta. Two distinct bright spots inside a crater appeared on the surface in imagery sent back by Dawn. The spots are likely to be highly reflective materials containing ice or salts. NASA then released a higher resolution image showing that instead of one or two spots, there are actually several.
Thanks for watching.
I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team.
Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.